Step 9A for packaging, terminal welding and enclosing for pouch cell. In this step, we connect the cell's terminals and enclose the stacked electrodes inside the pouch. First, the positive tab is welded to the cathode and the negative tab to the anode. At this stage, weld quality and alignment are critical, since inconsistent welds can lead to high resistance or mechanical failure later. Once the tabs are welded, the entire stack is inserted into the pouch. The pouch is then deep drawn, meaning it is shaped around the cell under high pressure, to ensure a tight, uniform fit. After insertion, 3 sides of the pouch are partially sealed, leaving one side open for electrolyte filling. Finally, it's important to avoid welding fully assembled cells directly to bus bars, as this can damage the terminal welds formed during this process. The images here show the sequence of tab welding, insertion, deep drawing, and partial sealing. Step 9B for packaging, canning and terminal welding. In this step, we place the finished jelly roll into a rigid housing, either prismatic or cylindrical, along with an insulating layer to prevent mechanical damage or electrical contact with the can. Once positioned, the housing is sealed, and the terminals are welded. Prismatic cells are welded to the lid's contact terminals, while cylindrical cells connect to the top and bottom of the can. After welding, capacitance tests are performed across all cell types. These tests help identify internal defects such as debris, separator folds or punctures, and burrs on the current collectors. The images on this slide highlight the sequence: inserting the jelly roll, adding insulation, sealing the housing, and final terminal welding. Step 10 for electrolyte filling. In this step, we introduce a precisely measured volume of electrolyte into the cell. A dosing needle injects the electrolyte while a partial vacuum helps draw the liquid deep into the internal structure. The system then applies an alternating pressure profile, vacuum, and inert gas backfilling to ensure full wetting of both electrodes. Wetting is critical. The electrolyte must penetrate the porous electrode coating uniformly to enable efficient ion transport. Maintaining extremely low moisture levels, ideally in the ppb range, is essential. Any residual water reacts with the lithium salt to form HF, which can damage the electrodes, lower performance, and pose safety risks. Because of this, the injection lines and storage tanks must be cleaned routinely to prevent residue buildup and contamination. After dosing and wetting, each cell is sealed to prevent exposure to ambient moisture. The images on this slide illustrate how electrolyte filling differs across pouch, prismatic, and cylindrical formats, but the core principles, accurate dosing, controlled pressure, and clean processing, are consistent for all cell types. Step 11 for formation. This is the first controlled charge-discharge cycle of the cell, and it is one of the most critical steps in determining long-term performance and safety. During this process, lithium ions intercalate into the anode's graphite structure for the first time, and the solid electrolyte interface, SEI, forms. A stable SEI is essential. It prevents continuous electrolyte decomposition, reduces irreversible lithium loss, and protects the anode during high-rate charging. The charging and discharging currents follow precisely defined voltage and current profiles. The equipment uses spring-loaded contact pins, shown in the diagram, to ensure consistent electrical contact with the terminals. Good carriers beneath the cells provide stable, conductive support, minimizing resistance variation from unit to unit. The formation environment, temperature, pressure, and contact quality directly affect SEI stability and internal resistance. As the SEI forms, small amounts of gas are generated, which is why you see the filled gas bag in the output image. Properly controlled formation results in a uniform SEI layer, lower internal resistance, and improved cycle life. Step 12 for degassing. In this step, we remove the gas generated during formation and complete the final sealing of the pouch cell. During formation, electrolyte decomposition and SEI growth create internal gases. These gases accumulate in the temporary gas bag attached to the pouch. Degassing begins by piercing the gas bag inside a controlled vacuum environment, allowing the gas to escape safely into an exhaust system that prevents environmental exposure. Once the gas is released, the pouch is resealed along the seam. Some processes add 1 or 2 folding operations to reduce the pouch height and reinforce the mechanical strength of the final seal. The objective is to leave no residual gas, maintain the mechanical integrity of the cell stack, and produce a high-quality, hermetic seal. This step is critical because poor degassing or weak sealing can lead to swelling, leaks, and long-term reliability risks. Step 13 for aging. In this step, the cells are placed in controlled storage to allow the SEI layer formed during formation to stabilize. This maturing period is essential because the SEI continues to evolve, and its stability directly affects capacity retention, internal resistance, and long-term safety. Aging can take several days to as long as 3 weeks, depending on the cell type and manufacturer requirements. The cells are stored at either normal or elevated temperatures, as shown in the images, and their open circuit voltage is regularly measured for quality assurance. These OCV measurements help identify abnormalities such as self-discharge, internal shorts, or electrolyte instability. Because large numbers of charged cells are stored together, safety is a major concern. Aging rooms are equipped with fire detection systems, nitrogen or deoxygenated environments, and cooling or suppression systems that prevent thermal runaway. IR cameras and fiber optic sensors monitor temperature trends across the racks to ensure no cell deviates from expected behavior. By the end of aging, each cell is fully stabilized, and its key performance characteristics, capacity, internal resistance, and self-discharge rate are verified before moving to final inspection and shipment. Step 14A for final control checks. OL testing. In the final control stage, each cell undergoes a comprehensive set of end-of-line tests to verify compliance with performance and safety requirements before shipment. We begin by confirming charge and discharge behavior, verifying that the cell delivers the expected capacity without abnormal resistance growth. One of the most important evaluations is the delta OCV rate test, which monitors the small voltage drop over several days. This drop reflects 2 intrinsic properties of the cell, the effective capacitance, CFF, and the self-discharge resistance, Republican South Dakota. Cells that show a voltage drop of 1.1 mV or less after 7 days are considered healthy, while larger drops indicate elevated self-discharge or internal defects. We then perform high-pot testing, applying a high potential to confirm electrical insulation and to detect internal shorts. Additional checks include cell trimming, mass and dimensional measurements, and, for pouch cells, leak and thickness inspections. Finally, every cell undergoes a visual examination to confirm tab quality, seal integrity, and overall surface condition. These OL tests collectively ensure that only stable, safe, and specification-compliant cells proceed to module assembly or customer shipment. Step 14B for EOL testing. In this final manufacturing stage, we verify that every finished cell meets the required electrical, mechanical, and safety standards before shipment. After aging, the cells are removed from their carriers and transferred to the end-of-line testing station. Each cell is discharged to its defined shipping state of charge, which also provides an accurate capacity measurement. Depending on the manufacturer, several additional checks are performed: DC internal resistance measurement, pulse power testing, OCV verification, leakage inspection, and optical surface checks. These tests confirm that the cell exhibits low self-discharge, stable capacity, and proper internal resistance, key quality characteristics shown in the table. Many production lines also include a grading step, where cells are classified into performance groups to support consistent module assembly. After passing the EOL tests, cells are protected with plastic covers, packaged in cartons, and released for shipment. This ensures safe handling, traceability, and stable performance throughout logistics and storage. Step 15A for pack process, module. The module stage is the first phase of the battery pack assembly process. In this step, finished lithium-ion cells are grouped, mechanically fixed, and electrically interconnected to form a stable module. These modules provide the required voltage, capacity, and safety features before advancing to full pack assembly for EVs or energy storage systems. Key activities include cell interconnection, linking cells in series/parallel to achieve the target electrical output. Structural integration, securing cells within frames or housings for mechanical stability. Thermal management integration, adding cooling plates or thermal pads to maintain safe operating temperature. Monitoring integration, incorporating sensors and harnesses for voltage, temperature, and current monitoring. Quality and inspection, verifying alignment, weld quality, insulation, and electrical performance. The table summarizes the major quality influencers: mechanical accuracy, electrical connection robustness, thermal management design, and the resulting quality characteristics: physical integrity, electrical performance, thermal stability, and overall safety. The included process diagram shows a typical prismatic cell module production line, from cell loading and inspection through stacking, busbar welding, and final module testing. Step 15B for battery pack, assembling for application. The battery pack stage integrates multiple modules into a fully functional energy system for EVs and other applications. While individual cells are limited in voltage and capacity, combining them into modules and then assembling those modules into packs provides the power, energy, and safety performance required for real-world operation. Modules are arranged in series to increase voltage and in parallel to increase capacity, depending on system requirements. The complete pack incorporates structural components, wiring harnesses, protection devices, and thermal interfaces to ensure reliable and safe operation. A critical part of the pack is the Battery Management System, BMS, which monitors voltage, current, temperature, and communication signals. The BMS manages state of charge (SOC), state of health (SOH), thermal behavior, and overall power optimization. The slide's images illustrate the progression from cell to module to pack and show how the BMS interfaces with the pack to ensure performance, longevity, and safety during charging and discharging. Safety. Safety is one of the most critical aspects of lithium-ion battery manufacturing because many process steps can unintentionally create conditions that lead to internal short circuits, thermal runaway, or fire. The single most common hazard is direct contact between the electrodes, typically caused by defects in the separator, misalignment during winding or stacking, or the presence of burrs and foreign particles introduced during mixing, coating, slitting, or cutting operations. Even small metallic contaminants, such as iron particles from worn tooling, can penetrate the separator during cycling and trigger a short. Process drift in coating thickness, calendering pressure, or electrode dimensions can also reduce the safety margin between layers. In addition, thermal or mechanical abuse, overcharge or overdischarge, and the gas generation stages of drying, formation, and degassing introduce additional risks if environmental controls are insufficient. Because these hazards can originate from personnel, methods, measurement systems, machines, materials, or environmental conditions, robust preventive measures are required at every stage. These include operator training, strict housekeeping to control dust and debris, routine inspection of tooling, frequent quality checks such as high-pot testing, and proper use of PPE, goggles, face masks, anti-static and fire-resistant clothing, gloves, and safety boots. Fire suppression systems and first aid resources must always be accessible. Overall, maintaining a disciplined safety culture and a strong quality control framework is essential for preventing internal shorts and ensuring safe, reliable cell production. Slide for production environment. This slide summarizes the environmental requirements across the full cell manufacturing chain, from slurry mixing through end-of-line testing. Each process step is executed under tightly controlled clean room and dry room conditions to prevent moisture and particle contamination, both of which directly affect cell safety, yield, and long-term performance. Electrode-related steps, mixing, coating, drying, calendering, slitting, and vacuum drying, are carried out in ISO 7-8 clean rooms, where the allowed number of airborne particles is strictly limited. Here, ISO 7 and ISO 8 refer to international clean room classes. ISO 7 permits up to 352,000 particles per cubic meter, greater than or equal to 0.5 m, while ISO 8 permits up to 3.5 million. These classifications ensure that foreign particles do not become embedded in electrode coatings, as such particles cannot be removed later and are a major cause of internal short circuits. Moisture control becomes increasingly strict as we approach cell assembly. The stacking/winding, packaging, and electrolyte filling areas operate in dry rooms with very low dew points, as low as -70°C, because even trace amounts of water react with the electrolyte to form HF, which reduces service life and poses a safety hazard. After cells are sealed, the requirements ease. Formation, degassing, and aging take place under controlled temperature and monitored safety systems, but no longer require extreme dryness. High temperature and normal temperature aging rely on precise thermal stability to allow the SEI layer to mature and to screen out defective cells. Overall, this slide illustrates how the production environment transitions from clean room, ultra-dry conditions during electrode fabrication and assembly to more conventional controlled environments during finishing processes, each stage tailored to protect cell quality and ensure manufacturing safety. The cost of LIB manufacturing. Battery manufacturing contributes roughly 1/4 of the total cost of a lithium-ion cell. Interestingly, despite this large cost share, manufacturing processes still receive far less R&D attention compared with active material development. Among all steps, mixing, vacuum drying, and especially formation/aging have the slowest throughput, ranging from hours to several weeks. This slow pace directly increases both operational time and overall facility cost. From a cost distribution perspective, the two dominant contributors are coating and drying, and formation and aging, which together account for nearly half, about 47%, of total manufacturing costs. Energy consumption shows an even sharper concentration. Drying/solvent recovery and maintaining the dry room environment alone make up about 76% of total energy use. These areas are therefore major targets for cost reduction strategies such as solvent-free coating, more efficient dryers, or advanced dry room systems. The accompanying charts clearly illustrate these contributions. Coating/drying and formation/aging are the most energy and cost-intensive steps in the entire line, followed by dry room operation. Understanding these bottlenecks is essential when evaluating process optimization or new manufacturing technologies. Challenges in LIB electrode production. This slide summarizes the major technical challenges in the electrode manufacturing stages of lithium-ion batteries. In mixing, achieving a uniform slurry is essential. Poor dispersion can cause particle agglomeration, non-homogeneous electrode composition, and unstable viscosity, all of which lead to coating defects downstream. In coating, the focus is on maintaining uniform thickness and width as the slurry is applied to the current collector. Variations in slurry rheology, machine behavior, or drying rate can disrupt coating uniformity. The industry is also exploring dry coating methods to reduce solvent use and energy consumption. During drying, solvent removal requires substantial energy and must be carefully controlled to prevent binder migration or gradients within thick electrodes. Improper drying directly affects adhesion, porosity, and long-term performance. Finally, calendaring compresses the dried electrode to achieve the desired density, porosity, and mechanical strength. The challenge is to optimize pressure to ensure uniform thickness without introducing defects, such as cracks or delamination. Together, these steps determine the final electrochemical performance, mechanical stability, and manufacturing cost of LIB electrodes. Future of mixing. Slide 1 of 3. This slide highlights the goal of reducing mixing cost by increasing throughput while keeping slurry uniformity high. Improvements focus on scaling up mixing methods and optimizing slurry composition, such as reducing solvent content to lower material cost and shorten drying time. The sequence of ingredient addition is also important. Adding PVDF and NMP before the active material supports better porous binder, carbon structures, whereas adding them afterward can reduce cell performance. The animation shows a rushed-in turbine, a radial flow impeller that provides stable, balanced mixing. It pushes fluid outward and circulates flow both upward and downward, enabling uniform dispersion, critical for consistent battery slurry quality. Future of mixing, Slide 2 of 3. This slide highlights how next-generation slurry mixing is evolving beyond conventional planetary mixers to achieve faster, more uniform, and scalable large-volume production. Modified high-shear mixing systems combine several impeller types to improve slurry homogeneity. A Rushton-type turbine provides strong radial flow, while an off-center helical ribbon impeller enhances axial, Z-direction, mixing. A stationary rectangular plate positioned near the vessel wall helps capture slow-moving regions and break up aggregates that typically accumulate there. This hybrid configuration is both cost-effective and scalable, producing a fully homogeneous slurry in about 2 hours. In NMC formulations, the improved dispersion has demonstrated performance gains of roughly 10 mAh per G compared to systems using only a Rushton turbine, illustrating how optimized mixing directly contributes to higher electrode quality and cell performance. Future of mixing, Slide 3 of 3. This slide introduces two emerging mixing techniques, ball milling and ultrasonic mixing, that help improve slurry uniformity and electrochemical performance. Ball milling is widely used for both dry powders and slurries. During milling, particles form beneficial agglomerates due to surface energy interactions. For example, C65 and PVDF can cluster between LCO particles, improving ionic pathways. In silicon-based anodes, ball milling has shown meaningful performance gains. One study reports that capacity retention improved from 65% to 84% after 20 cycles, compared with conventional stirring. Ultrasonic mixing, shown at the bottom, uses microbubble collapse and microturbulence to disperse materials effectively, even at high solid concentrations. Because it does not rely on a mechanical stirring rod, it consumes less energy and offers strong potential for high viscosity, next-generation slurries. Overall, these advanced techniques enhance homogeneity, improve electrode utilization, and improve long-term cycling performance. Future of coating, drying, and solvent recovery, Slide 1 of 2. This slide highlights future directions to lower the cost and energy burden of coating, drying, and solvent recovery, three of the most energy-intensive steps in LIB manufacturing. Traditional cathode production relies on NMP, a costly and toxic solvent with a high boiling point, which drives long drying times and accounts for nearly half of the total process energy. Reducing solvent content can dramatically speed up drying. Higher solid loading can increase drying rates by up to 80%, but also increases slurry viscosity, requiring specialized slot die configurations and higher pressure. A major research direction is replacing NMP with water-based binders such as cellulose or lignin derivatives. These systems can eliminate the need for solvent recovery equipment and increase throughput, but they introduce challenges. Many cathode chemistries react with water, potentially corroding the aluminum current collector. pH adjustment strategies, such as adding phosphoric acid, help mitigate corrosion but currently cause significant capacity loss. The images illustrate three emerging coating approaches: continuous stripe coating, intermittent patch coating, and pattern coating, each designed to optimize material deposition and reduce drying demands. Future of coating, drying and solvent recovery, Slide 2 of 2. This slide introduces emerging solvent-free electrode manufacturing technologies designed to cut costs, reduce energy use, and eliminate NMP from the coating process. Maxwell Technologies has demonstrated a dry electrode process in which well-mixed powders, active material, conductive carbon, and binder, are calendared into a self-supporting film. This film is then laminated directly onto the current collector, eliminating the need for slurry preparation, drying ovens, or solvent recovery systems. The result is lower manufacturing cost, improved sustainability, and competitive energy density and cycle life. Additional solvent-free approaches include dry spray coating and electrostatic powder deposition, followed by hot pressing, which similarly avoid the high energy burden associated with NMP evaporation. Overall, these technologies represent a major step toward greener, faster, and more cost-efficient electrode production. Future of slitting. this slide highlights how slitting technology is evolving to improve precision, edge quality, and overall throughput while keeping costs controlled. Laser cutting has become a strong candidate to replace traditional mechanical slitting because it delivers very clean edges with minimal deformation and excellent burr-free quality. Infrared fiber lasers can achieve throughputs of around 30 m/min at low power consumption, about 54 W, making them a fast and efficient option. Green lasers provide even tighter clearance control, below 20 micrometers, which significantly reduces the risk of internal short circuits, though their throughput is slower at around 4.5 m/min. A key consideration is that laser cutting may generate fine metallic debris, which can lead to lithium dendrite formation if not properly mitigated. Therefore, while laser slitting provides substantial quality and control advantages, effective debris management and cleaning systems are essential for safe and reliable battery production. Future of welding. In this slide, we look at next-generation welding technologies that aim to improve tab joint quality, reliability, and safety while keeping costs under control. As battery operating temperatures can reach 80 degrees Celsius, welded joints are subject to thermal expansion and mechanical fatigue, making robust joining methods essential. Ultrasonic welding is widely used for pouch cells because it consumes little energy and can join dissimilar materials, although it is limited by joint thickness and heat generation. Tesla's wedge-bonded, tabless approach is an evolution of this concept, reducing internal resistance and improving energy density. Resistant spot welding remains common for cylindrical and prismatic cells due to its low cost, but it struggles with highly conductive or dissimilar materials. Laser welding provides the highest joint quality, with excellent tensile strength and the lowest contact resistance. Its challenge is joining dissimilar materials, which has motivated research into shorter wavelengths and pulse widths. The image here illustrates a laser welding system used in cell manufacturing. Future of formation and aging. Concise and professional. This slide highlights emerging approaches to shorten formation and aging while preserving SEI stability and long-term cell performance. Traditional formation relies on multiple low-rate charge/discharge cycles to build a uniform SEI. However, increasing the charge rate too aggressively can lead to uneven SEI growth or lithium plating due to high polarization. Promising strategies include lowering the upper cutoff voltage from 4.2 V to 3.7 V, which can have formation time for LCO/graphite cells without compromising cycling stability. Another method is conducting formation at high SOC, 3.9 to 4.2 V, which enables SEI formation in about 14 hours while maintaining performance. Pulse current formation is also gaining traction. By alternating brief high-rate charging with rest periods, heat generation and polarization are reduced, allowing faster SEI development with minimal degradation. Overall, these methods focus on accelerating formation time while ensuring a high-quality SEI layer that supports long-term safety and cycle life. Manufacturing process summary. This slide provides a high-level overview of key manufacturing processes, highlighting recent development efforts, their benefits, and the challenges limiting industrial adoption. The tables show that although many innovations, such as advanced mixing methods, dry coating, laser slitting, and pulse current formation, offer clear advantages in cost, throughput, and performance, most have not yet been widely implemented due to scalability, equipment costs, or unresolved technical risks. A good example is the manufacturing of a dry electrode. It significantly reduces energy consumption and eliminates solvent recovery, but requires new equipment, careful powder control, and optimized binder distribution. Despite these challenges, Tesla's acquisition of Maxwell demonstrates that dry manufacturing is viewed as one of the most promising breakthroughs. Overall, the slide emphasizes that meaningful progress in next-generation LIB manufacturing will depend on solving scale-up challenges and accelerating industry adoption of these emerging techniques. This marks the end of the lecture on Chapter 4, Lithium-Ion Battery Manufacturing. We'll meet again in the next lecture, which is the second part of Chapter 4 about the schematic overview of Li-ion battery manufacturing. Thank you. We'll meet again in the next lecture.